Hey everyone, and welcome. So today we're going to peek under the hood of a system that most of us Python developers just take for granted: memory management. We're going to peel back those layers of abstraction and see what CPython is actually doing with your computer's memory. Let's dive in. I bet you've seen this before, right? You've got a service that runs for a long time, and you watch its memory footprint just creep up and up and up. You know objects have gone out of scope. You've deleted variables, but the memory that the operating system sees never seems to go down. And look, it's not just you. This is a classic Python mystery, and today we're going to solve it. You know, one of the best things about Python is that you don't have to worry about memory. It just handles it. Unlike in a language like C or C++, where you're agonizingly calling malloc and free for every little thing, this convenience is amazing. But it hides this really complex, really sophisticated system working behind the scenes. And understanding that system, well, that's the key to our whole memory mystery. All right, to really get this, we've got to zoom way down. I mean, all the way to the C level. Because let's not forget, CPython is at its heart a C program. And in that C world, every single thing you think of as a Python object, an integer, a string, a list, you name it, it's actually just a C struct. And this is the absolute foundation of everything, the PyObject. It's a pretty simple C struct that's at the very beginning of every single Python object in memory. And it holds two absolutely crucial things: a pointer to the object's type, so Python knows if it's looking at an int or a list, and this other thing called obrefCount, the object's reference count. And that little number is basically how Python knows when it's time to take out the trash. Okay, so check this out. Here's a fun little Python puzzle for you. If you take the number 100 and assign it to two different variables, a and b, they actually point to the exact same object in memory. But if you do the very same thing with the number 257, you get two completely separate objects. So what gives? Why does that happen? Well, the answer is actually a super clever optimization. Python knows that we use small integers all the time. So to save memory and speed things up, it just creates objects for all the integers from -5 all the way up to 256 when the interpreter starts. So anytime you use one of those numbers, Python just hands you a pointer to the one that already exists. And this is our first big clue that Python's memory game is all about being smart and efficient. All right, let's dig into that reference count we mentioned. This is Python's #1 strategy for garbage collection. The idea is actually pretty simple, but it's incredibly powerful. Every single object just keeps a running tally of how many different names or references are pointing at it. So when you create a new object, say x equals my object Python carves out some memory for it and sets its reference count to 1. Easy enough, right? The variable x is the one and only thing pointing to it. Okay, but what happens if you make another variable point to it, like y equals x? You're not making a copy, you're just giving the same object another name. So Python just finds that object in memory and bumps that little counter up to 2. And here's the magic. This is the whole point. The second a reference goes away, maybe a function ends and its local variables disappear, or you just type del x, that count goes down. The second that counter hits 0, boom. Python knows nothing in your program is using that object anymore, and it can instantly wipe it out and reclaim that memory. It's super fast, super predictable. Okay, so reference counting tells Python when to clean up. But where did that memory even come from to begin with? Well, that brings us to the next layer of the onion, a special custom-built memory allocator called Pymalloc. And you might be wondering, wait, the operating system already knows how to manage memory, right? It's got things like malloc. So why on earth did the Python developers build a whole separate system just for Python objects? The answer, in one word, is speed. Talking to the operating system kernel is what we call a system call, and it's a relatively slow, expensive operation. Now, think about how many tiny objects a Python program makes. If Python had to bother the OS for every tiny little integer or string, the whole thing would slow to a crawl. Pymalloc is the solution to that bottleneck. So how does it pull this off? I want you to picture it like this. Pymalloc doesn't go to the OS for a small box. No, it asks for a giant 1 megabyte warehouse, and we call that an arena. Then it carves up that warehouse into different sections with bookshelves, which we call pools. Each pool is for books of a specific size. You know, a pool for 8-byte objects, a pool for 16-byte objects, and so on. And finally, the individual slots on those shelves where the objects actually live, those are the blocks. It's this whole system that lets Python manage tons of small objects without constantly bugging the OS. But here's the catch. Pymalloc has one golden rule, and you gotta remember this. It only handles the small stuff. Specifically, objects that are 512 bytes or less get to use this fancy arena system. For anything bigger than that, Python just says, you know what, for something that big, the cost of a system call is fine, and it goes and asks the OS for the memory directly. All right, we've got all the puzzle pieces now. We know about reference counting, and we know about Pymalloc with its arenas and pools and blocks. So let's circle all the way back to that first question we asked. Why does my app's memory just keep growing? And this right here is the smoking gun. If you remember one thing from this whole explainer, make it this sentence. Python will only give that big 1 megabyte chunk of memory, that arena, back to the operating system when every single block inside of it is totally, completely, 100% empty. So just think about what that really means for a second. Your app handles a request, creates thousands of little objects, they all fill up an arena. The request finishes, and 99.9% of those objects get cleaned up. But if just one tiny object, maybe some little piece of a global cache, is left behind, it acts like an anchor, holding that entire 1 megabyte arena hostage. The memory's free from Python's perspective, but it can't be given back to the OS. That is memory fragmentation, and that is why your process memory rarely shrinks. Okay, so we get the why now, but how do we actually find the culprit? How do we hunt down these memory issues in our own code? Let's talk tools. For most of us working in Python, you've got two main weapons in your arsenal. The first is Tracemalloc. It's built right into Python, it's pretty lightweight, and it's perfect for seeing where your memory is growing over time. Your other option is a third-party tool like Guppy. Now, this one is a bit more of a heavyweight. It takes a complete snapshot of every single object in memory, which can be intense, but it lets you do some incredibly powerful analysis on what's holding on to what. So a really common pattern with Tracemalloc is to take a snapshot, run some code that you think is leaky, and then take a second snapshot and compare them to see exactly what new objects were created. But what if the leak isn't in your Python code? What if it's in a C extension? Well, for those nightmare scenarios, you gotta break out the big guns, like the GDB debugger. And luckily, the Python team gives us a handy script that actually teaches GDB how to understand Python's internal objects, which makes that whole process way less painful. You know, to really appreciate Python's approach, it helps to see what the alternative looks like. So let's zoom out for a second and compare it to another hugely popular system, the Java Virtual Machine, or JVM. This table really shows the different philosophies at play. On one side, you have Python. Its whole game is reference counting. The big win, when an object's not needed, it's gone. Instantly. It's predictable. The downside is that tiny bit of memory overhead for the count on every object. Then you've got the JVM. It has a totally different philosophy. It uses what's called a tracing garbage collector. It just lets the garbage pile up for a while. Then, every so often, it yells, "Everybody freeze," what we call a stop the world pause. And it goes on a cleaning spree, figuring out what's still in use. It can be faster overall, but those unpredictable pauses can be a real problem for some applications. Wow, okay. So we've gone from a simple question about memory growth all the way down into the guts of CPython with PyObjects and Pymalloc arenas. So what are the big takeaways? 1, Python cleans up immediately using reference counting. 2, for small stuff, Pymalloc is king, grabbing memory in big chunks to stay fast. And 3, that memory leak you're seeing, it's probably just fragmentation, one tiny object holding a giant 1 MB arena hostage. Having this mental model is a complete game changer. So the real question is, now that you know this, how is it going to change the way you write and debug your code?